B, 1 is associated with B, but when you send, say, 3, you will not get A, you will get B, because B has the higher level of this modulation. So what I'm saying, that you can really get this universal architecture without memory buffer, just by playing with the levels of an analog memory, which is plentiful. And this changes a lot of things. Do I make any sense? Do you understand what I'm saying? Okay, good. Good, because it's real effect. It's real effect. You can replace system with random access buffer by system which has only programmable read-only memory and has this analog memory which biases this programmable memory. And this is a kind of good way for the brain to do this thing. The reason for that I will explain later. So first of all, I showed you that just without memory buffer, I got universal architecture, universal Turing architecture, which means it's a different architecture. It's a different type of computer, universal programmable computer, which can be programmed by simply forcing it to do something, which means you force or at random if the robot did the right behavior somehow, and this behavior is reinforced, then that's it. Robot got the right software, which means I'm saying that with this approach, software and behavior is almost the same thing. You don't need to program the system to do things. You need just to stimulate it to do the right behavior. And then, if this behavior is stored in some way, like I showed you, there are many other continuation of that, but in some simple way, this behavior, if it is stored in memory, that's it, system is programmed. And now you can at least understand in general, outline, how we can get so complex. Because suppose we start with some relatively simple software in the form of these associations, which forces us to do more or less right things. And then, of course, we make mistakes. And there is another system, which I'm not talking about here, system of reinforcement in the brain. Okay, so once you form this state of long-term memory, you're already programmed to do that, which means just by accumulating your experience, you're getting software, which allows you to do more complex behavior. You do more complex behavior, you get more complex software in your memory, and you become more complex system, and there is no end to this evolutionary software development loop. And this is not possible with memory buffer, because with memory buffer, you would have to learn how to use memory buffer, and there is no way you learn to. In this case, it's done automatically, because memory buffer is always kind of activated in a way so it reflects that the latest event is more excited. And this produces the same effect as if you rewritten the symbol in that. Does it make sense, right? Okay. Anyway, but it has much bigger implication than that. So first of all, we got universal architecture. We don't use memory buffer, which is very important. We got effect of working memory, which means this robot really sees this tape. And this explains, by the way, how I can play chess mentally. Because I don't, if I play chess, oh boy, what is that? My clock is, oh, okay. Okay, so if I'm playing chess, I somehow can move pieces on the board, right? And when I moved it, when I return to this position mentally, I see the new piece which I placed it, which is exactly effect of random access memory. Okay, but why it is good to have this memory in this stupid way, kind of, instead of just simply writing and rewriting? I told you one reason. First of all, you cannot learn to use RAM. There's no way. Like say if you memorize, if say processor in this computer would memorize all its actions, it would not create software which would run this computer again. You need much more structured software. In the case you do it this way, you just showed how to do something and you created software, which does that. But much more than that. Okay, let's concentrate on this thing. And this was neurophysiologist Zopf Jr. in 1961, who said, I don't believe in all this artificial intelligence and all these things, because humans can do combinatorial number. And that is a very interesting article, Attitude and Context, you may find it. He said, humans differ from computers because we can do combinatorial number of different activities. And you guys, you're simulating only some small number of these activities, which means you're simulating enormously small part of the human behavior. And it doesn't matter that you simulate 100 or 1,000 or millions, because we are talking about more activities, possible activities, than there are atoms in the universe, much more. Okay, so how this activation of the programmable memory would explain this phenomenon? Okay, very simple. Suppose I have this table which has all associations needed to create two input, one output Boolean functions, right? In this case, I spent, in this case, 8 locations of memory, right? And there are 16 Boolean functions. So I can select some of these elements of this table, and I get Boolean function, right? And I'm showing you, if you select something which is shown on the top, you get XOR. If you select something in the second row, like 0, 1, and 2, and 7, you get AND, and so on. And in fact, you can even get kind of noisy AND, which means which will be probabilistic Boolean function. Okay, in this case, no big deal, because I spent 8 locations of memory, which is 2M. M is the number of inputs, and in this case, there are only 2 outputs, right? So, but I got 2 to the power of 4 Boolean functions. Suppose, however, I have M inputs, 10 inputs, right, in this table. I will need to spend 2 multiplied by 2 in the power of 10, which means I will spend 2048 locations of memory only. How many Boolean functions now I can get? I will get this n, 2 to the power of 1,024, which is an enormous number. This tells you something, how the brain achieves this, not just universality, but how it achieves this configurability, reconfigurability. If you have software of the size only 2, like in this case 8 location, by correctly reactivating this software, you get functionality for 2 to the power of that number of locations, which means the only thing we need to explain how actually this is happening. And I claim it's a complex thing, you really need to think hard about it, that really inputs and your own behavior will activate your memory in such a way that just the appropriate part of your knowledge will participate. And because you can reactivate, change your, well, and this is what you can call mental set. So depending on, it's not just depending on what you know, but depending how you activate what you know, you become different system. And in the previous lecture, we saw that effect of mental set. People have mental set that, okay, that technology is produced doomsday scenario, right? Okay, but some people may have a different mental set. Some other people may have even some another set. And in fact, for you to understand what mental set is, I'll give you this example. I'll ask you this question. You probably know American history. What American presidents are not buried in American soil? Can you quickly answer this question? Bush is not buried. You see, what happened? What happened, because I said what presidents are not buried, is not important. It doesn't produce much activation. But buried produce activation in your memory of the knowledge which is associated with death. So you're searching your memory for the dead presidents, and that's why there's delay. And you know perfectly well that there are alive presidents which are not buried in America. So, but you don't consider this possibility because your memory is activated. And in fact, you can, by activating your memory in many different ways, you can produce different mental set and different attitudes to the same information. And this has fundamental implications, for example, for pattern recognition. Because suppose I made this classification. I use backpropagation. I don't know how many of you know some other optimization algorithm. By the way, all those neural networks will be of type 4, so which is not a big deal. But anyway, suppose I produced optimal classification of faces or whatever. But then context changes. Yeah, suppose I learned to separate books from disk drives, right? I built system which does, in whatever way, perfect classification. But then I change context. I ask a question. Take this. In this take this context, it's no longer important that this is book or this is disk drive. What is important is the size of that. What I'm saying, that asking different questions about what you perceive changes your attitude and changes the required actions to that. And if you calculate how many of this possible attitude you can create, you get again this combinatorial explosion, which means if you build optimal classifiers, you cannot build optimal classifier for all possible contexts. You can only activate whatever limited knowledge you have, so it matches this context. That's extremely important. Because, for example, if you have C++ program, you cannot take a marker and just strike this, strike this, strike this, strike this, the system breaks, right? But with the low-level software, like these associations, you can do that. You strike this, 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 and it's still perfectly valid and stable performance. This idea, in fact, can be developed very far. You can get statistical filtering, and I'm not really even touching this, scratching the surface of this iceberg. But we are coming to a completely new approach to that. That, first of all, we create this stupid software just without really programming in C, writing compilers, because it's not available in the brain. We are creating associations, and those associations are perfectly, as I showed you, perfectly universal programming language, which means you can program system to do anything. But more than that, those associations can be reconfigured on the fly in combinatorial number of ways, which means by creating relatively short software, you can reuse this software in enormous number of ways by simply reactivating it, which is really the topic of that. Okay, so I call these systems E-machines. The reason for E, because E stands for excitation or residual excitation. There was a neurophysiologist back at the beginning of the century who was actually saying into intuitive terms what now I'm saying in this explicit terms.